Emmy Noether's theorem, presented in 1918, stands as a cornerstone of modern theoretical physics. This profound result, born from the crucible of early 20th century mathematics and physics, establishes a deep connection between symmetry and conservation laws, a link so fundamental that it permeates the fabric of our understanding of the universe. Its genesis lies within the burgeoning field of variational calculus and the challenges presented by Einstein's newly formulated theory of general relativity. Noether's theorem provides a rigorous mathematical framework for understanding why certain quantities, such as energy, momentum, and angular momentum, remain constant over time. It is a testament to the power of abstract mathematical reasoning to illuminate the deepest secrets of the physical world. The intellectual landscape preceding Noether's work was dominated by the calculus of variations, a field concerned with finding functions that optimize certain integrals. Think of finding the shortest path between 2 points, or the shape of a soap bubble minimizing surface area. These problems, while seemingly disparate, share a common mathematical structure. Mathematicians like Euler, Lagrange, and Hamilton had developed powerful tools for tackling such variational problems, but these tools lacked the generality and abstractness needed to address the complexities arising in relativistic physics. Einstein's general relativity, with its curved spacetime and coordinate invariance, presented a particularly thorny challenge. The usual conservation laws appeared to be violated in this new framework, leading to considerable confusion and debate. The problem stemmed from the fact that general relativity is invariant under arbitrary coordinate transformations. This invariance, while a fundamental feature of the theory, made it difficult to define conserved quantities in the traditional sense. It was in this context that Felix Klein, seeking to resolve these difficulties, invited Emmy Noether to lend her mathematical expertise to the problem. Klein recognized Noether's exceptional ability to abstract and generalize mathematical concepts, a talent that would prove crucial in unraveling the intricacies of conservation laws in general relativity. Noether's theorem, in its most general form, states that for every continuous symmetry of a physical system, there exists a corresponding conserved quantity. A continuous symmetry refers to a transformation that leaves the equations of motion of the system unchanged. For example, the laws of physics are believed to be the same at all times, which is an example of time translation symmetry. The theorem provides a precise mathematical recipe for constructing the conserved quantity associated with a given symmetry. This construction involves identifying the infinitesimal generator of the symmetry transformation and then using the Euler-Lagrange equations to derive the corresponding conserved current. The integral of this conserved current over a spatial volume yields the conserved quantity. To unpack this further, consider the example of energy conservation. The laws of physics are believed to remain the same whether the experiment is performed today, tomorrow, or next year. This is time translation symmetry. Noether's theorem tells us that corresponding to this time translation symmetry, there is a conserved quantity called energy. Any system that appears a violate energy conservation does so because there are unobserved symmetries that are unaccounted. Similarly, the translational symmetry of space, that is, the laws of physics, are believed to remain the same whether we are in New York or in Los Angeles, leads to the conservation of momentum. Rotational symmetry leads to the conservation of angular momentum. These are not mere coincidences, but rather deep consequences of the fundamental symmetries underlying the laws of physics. The immediate impact of Noether's theorem was profound. It provided a clear and unambiguous resolution to the problem of conservation laws in general relativity. The theorem demonstrated that the apparent violation of conservation laws in general relativity was a consequence of the theory's coordinate invariance. The conserved quantities were not simply constants, but rather quantities associated with specific symmetries of spacetime. It provided physicists with a powerful tool for identifying conserved quantities in any physical system, regardless of its complexity. Its application extends beyond classical physics into quantum field theory, where symmetries play an even more crucial role. In quantum field theory, Noether's theorem provides the link between symmetries and conserved currents, which become associated with particles. For example, the conservation of electric charge is associated with a symmetry known as gauge invariance. The corresponding conserved current describes the flow of electric charge, and the associated particle is the photon, a mediator of electromagnetic interactions. Similarly, other fundamental symmetries in particle physics, such as the weak and strong interactions, are associated with conserved quantities and corresponding particles. The standard model of particle physics, our most successful theory of fundamental particles and forces, is built upon the foundation of Noether's theorem and the crucial role of symmetries. The influence of Noether's theorem extends far beyond physics into other areas of mathematics and science. In mathematics, it has led to a deeper understanding of the relationship between groups, algebras, and invariant quantities. Her work has had a major influence on the further development of abstract algebra in engineering. Noether's theorem is used in the design of control systems and the analysis of complex systems. The theorem provides a framework for identifying conserved quantities, which can be used to simplify the analysis and design of these systems. Despite its profound impact, Noether's theorem was not immediately appreciated by all. The mathematical formalism was initially intimidating to some physicists, and the abstract nature of the theorem made it difficult to grasp its full significance. Moreover, Noether's gender presented a significant obstacle to her acceptance. Within the male-dominated academic world of the early 20th century, she faced discrimination and prejudice throughout her career, and it took many years for her contributions to be fully recognized. The initial rejection of Noether's work is a reminder of the biases that can exist within the scientific community, and the importance of ensuring that all scientists, regardless of gender or background, have the opportunity to contribute to our understanding of them. Over time, however, the power and elegance of Noether's theorem became undeniable. Physicists and mathematicians alike came to recognize the theorem as a fundamental result with far-reaching implications. It is now considered one of the most important theorems in modern physics. Its continued use in research and its foundational role in theoretical understanding speak to its timeless quality. Subsequent work has built upon Noether's theorem in numerous ways. For example, the concept of supersymmetry extends Noether's theorem to include symmetries between bosons and fermions, the two fundamental types of particles in nature. Supersymmetry predicts the existence of new particles that have not yet been observed experimentally, but it remains a vibrant area of research in theoretical physics. The development of quantum field theory has also led to generalizations of Noether's theorem to include gauge symmetries, which are symmetries that are local in spacetime. These gauge symmetries are fundamental to our understanding of the fundamental forces of nature. The Batalin-Vilkovisky formalism is an advanced technique used in theoretical physics that leverages Noether's theorem in complex systems with gauge symmetries, further demonstrating the theorem's enduring and evolving role. Noether's theorem also has connections to other important results in mathematics and physics, such as the Bellin-Fante-Rosenfeld tensor, which provides a way to define a symmetric energy-momentum tensor in field theory. This tensor is important for understanding the gravitational properties of matter. In the realm of general relativity, the comma integral, inspired by Noether's approach, provides a way to compute the mass and angular momentum of a stationary spacetime from integrals over its boundary. These related concepts highlight the interconnectedness of various mathematical and physical ideas stemming from Noether's initial insights. The story of Emmy Noether and her theorem is a testament to the power of mathematical abstraction and the enduring importance of fundamental symmetries in physics. Despite facing considerable adversity, Noether persevered and made groundbreaking contributions to our understanding of the universe. Her theorem continues to inspire and guide physicists and mathematicians today, serving as a reminder of the profound connection between mathematics and the physical world. It is a theorem so fundamental that it shapes our understanding of reality at its deepest level, a legacy that ensures Emmy Noether's place among the giants of science.